Fiber-reinforced polymer matrix composites, or PMCs, are widely used in the aerospace industry. These materials are lightweight and have excellent mechanical properties. Unfortunately, all composites are susceptible to heat damage when exposed to elevated temperatures, causing significant and irreversible loss of mechanical strength properties. This can seriously affect the flightworthiness and safety of the aircraft. Detecting and quantifying heat damage in composites has been a major concern for the aerospace industry for over 20 years. Galt Technologies and the Oak Ridge National Laboratory, under sponsorship by the Office of Naval Research, has developed a composite heat damage detector based on laser-induced fluorescence that can measure the extent of heat damage in several composite materials widely used in military aircraft. The Laser-Induced Fluorescence, or LIF, composite heat damage detector is a commercially available, non-destructive, portable, and lightweight inspection instrument that provides rapid, reliable, and reproducible detection of incipient heat damage in composites. Fluorescence occurs when light interacts with a material, resulting in the emission of longer wavelength photons. Specifically, an excitation source causes the material to become electronically excited. Subsequent emission of light from this excited state can be monitored to reveal molecular properties of the material. Because LIF is sensitive to the molecular structure of the chemical compounds being studied, very small changes in the LIF emission spectrum can be used to both detect and quantify heat damage in composites. Earlier studies at Oak Ridge National Laboratory demonstrated that many of the composites used in the aerospace industry are fluorescent over a wide range of excitation wavelengths. The composite heat damage detector uses an eye-safe diode laser operating at 405 nanometers to induce fluorescence over a range of several hundred nanometers. Fluorescence is then collected and directed to a spectrometer where the light is dispersed across a multi-channel linear array photomultiplier tube, or PMT. The PMT output is monitored by an analog to digital converter and sent to a laptop computer for data analysis and display. Close examination of the LIF emission spectrum allows the instrument to correlate changes in the spectra to mechanical strength properties of the composite. This is achieved by correlating heat damage to changes in the LIF emission spectra for a series of carefully calibrated composite test panels that have been subjected to a wide variety of known elevated temperatures having known mechanical strength properties. There are two major components of the laser-induced fluorescence composite heat damage detector, including the LIF unit and a laptop computer. The laptop runs custom software that provides a graphical user interface to the LIF unit. The LIF unit contains the excitation laser, the spectrometer, photomultiplier tube, detector electronics, analog to digital converter, and power supplies. A flexible reflection probe is used to deliver the diode laser excitation and recover the induced fluorescence. Use of a flexible probe allows the user to detect and monitor heat damage in remote or limited areas. This probe is comprised of 7 200-micron optical fibers and a 6:1 geometry. The central fiber is used to deliver the diode laser light, while the 6 surrounding fibers are used to recover the LIF emission and return it to the LIF unit for detection and processing. The reflection probe tip is mounted in a custom holder that both protects the fiber optics and positions the tip for optimal collection efficiency. Inside the LIF unit, light is coupled from a diode laser to the central fiber optic, while the 6 collection fibers are directed to the spectrometer for dispersion and detection. While the diode laser is a Class 3B device and capable of emitting up to 50 milliwatts, the laser is operated such that light exiting the diode laser does not exceed 5 milliwatts. Additionally, the light exiting the F11 probe diverges rapidly. Any incidental light emitted from the probe or reflected off an aircraft surface is completely eye-safe. A commercial laptop computer operates a custom software package that interfaces to the LIF unit via USB. This allows the computer to be physically separated from the unit. A typical application might be locating the LIF unit and laptop computer on a mobile cart, which can be transported to the aircraft being studied. The graphical user interface allows the user to control the LIF unit, and it provides a real-time display of the LIF emission spectrum, along with a correlation value that provides an indication of the amount of strength loss and the severity of heat damage of the material under investigation. It also provides a percent damage factor, which we have defined as a percent residual of the mechanical strength properties of a non-heat damaged or baseline composite. Deviation from this baseline over a certain percent value, which is determined by the design allowable of the particular material, causes the display of the percent damage factor to reverse colors and activates an audible alarm, alerting the user that the material is heat damaged beyond an acceptable level. Most aspects of the LIF unit are hidden to the end user. Modulation frequencies, voltage drive levels for modulation, and diode laser output, for example, are assessed through higher-level password-protected software commands. The graphical user interface will not provide feedback or damage level until the user has selected the material to be investigated. The only other required input is to set the photomultiplier gain level. The LIF unit is comprised of a diode laser excitation source, a spectrometer, a 32-channel linear array photomultiplier tube, and detector electronics, an analog-to-digital converter, laser power supply, main power supply, and reflection probe. The front panel of the LIF unit was designed to have minimal input from the end user. A key switch is used to activate the diode laser power supply, while a push-button switch is used to activate the software-controlled modulated output of the laser. An LED indicator is used to alert the user that the laser output is activated. The only power requirements for the LIF unit is a standard 110 volt AC. An AC-DC power supply supplies low-level voltage to the analog-to-digital converter and detector electronics. The laser power supply provides the necessary voltage levels to the diode laser. The modulation voltage is set by software and is provided via one of the DAC channels on the analog-to-digital converter. This modulation voltage is input into the laser power supply unit. A commercially available 405 nanometer 50 milliwatt diode laser module was used in construction of the LIF unit. The maximum output power is determined by the user via password-protected software menus and is preset at the factory to a maximum of 5 milliwatts in order to certify the unit as a Class 3A or iSafe device. The diode laser has an SMA connector output, which is used to launch excitation light into the reflection probe. Fluorescence collected by the reflection probe is input into the spectrometer by the 6 collection fibers, which are terminated in a custom SMA connector. This connector positions the 6 linearly arrayed fibers for input into the spectrometer. A 200 micron slit inside the spectrometer helps filter unwanted ambient light. A grating is used to separate the optical components of the LIF emission spectrum, and a mirror is used to focus the dispersed light across a 32-channel linear array detector. The analog-to-digital converter in this case is a commercially available unit from National Instruments. It performs 12-bit digitization at rates up to 1.2 MHz and is used to both supply the modulation waveform to the diode laser power supply, as well as digitize output from the detector electronics and direct LIF information to the laptop for processing. A 32-channel linear array photomultiplier tube, or PMT, is used to detect the optical output of the spectrometer. For this application, a PMT is ideal due to its high gain and bandwidth characteristics. An optical filter is used to reject backscattered laser light that makes its way from the sample surface to the spectrometer. The PMT and optical filter are located on a custom detector board. Laser-induced fluorescence emission exiting the spectrometer is detected by the PMT and converted to voltage by shunt resistors located on the detector board. A high-voltage power supply, also located on the board, provides high voltage levels required for operating the PMT. Low-level voltages required as input to the detector board are provided by a DAC channel on the analog-to-digital converter and are controlled via software. The laser-induced fluorescence composite heat damage detector uses software to perform a digital demodulation of the collected and stored waveforms for each of the 32 optical channels. The laser is modulated at approximately 30 kHz. Quadrature demodulation of the LIF signal collected by the photomultiplier tube reduces interferences from ambient light by moving the signal of interest to a more quiescent region of the noise spectrum.